We are talking about chapter 10, which is on rotational motion and angular momentum in this video. So we need to start out discussing how the shape of an object can influence its rotational inertia and how that influences its rotational momentum. So rotational inertia is the rotational equivalent of mass. At one point in a previous video, we talked about how torque was the rotational equivalent of force. Well, moment of inertia is the rotational equivalent of mass. And we will, in a future video, look at how you can write a linear equation and then translate it into an angular equation by replacing all the m's with moments of inertia, all the forces with torques, and so on. So just a spoiler alert, things to look forward to. All right, so the moment of inertia in general form is always symbolized by capital I, and it is equal to the sum of mr squared, where m is the mass, and r is the distance that mass is from the axis of rotation. So you can have an object and rotate it in different ways. So for example, if you had a pencil could be allowed to roll down an incline, and its axis of rotation would be the lead in the pencil along the long axis. So all the little bits of mass would be really close to that axis of rotation. So the R's would be very tiny. You could take that same pencil and instead of having it roll down the ramp, you could drill a little hole in it and spin it like the propeller on a plane. We could stick a pin through the middle and spin it like a propeller, or like a baton. When I was a little girl, I had a baton. And in that case, some of the mass would be close to the axis of rotation, but at the ends, that mass would be a long distance from the axis of rotation. So one object rotated in different ways will give you different moments of inertia. The moment of inertia, so for different axes of rotation on the same body, we've just mentioned that. Also, we need to look at how the mass is separated. So in our example with the drawing, you have two discs that have the same mass, but disc A is fat and disc B is flattened out. So on disc A, R is a small number, disc B, R is a larger number. So you can see that the larger the R, the greater the moment of inertia. In our equation, the greater R is going to have the greater moment of inertia, assuming the mass is the same in both cases. So if we look at these two, which one's going to be more difficult to stop spinning? Well, I know we haven't talked about it yet, but let's think back to what we know about inertia. So if you have an automobile and a tricycle, the automobile has the larger inertia. Remember, inertia is related to mass and allows an object to obey Newton's first law. A body at rest stays at rest. One in motion stays in motion. So the more mass you have, the more inertia you have. So the car would have the larger inertia. The tricycle would have the small inertia. If they were both rolling downhill, which one would you be willing to step in front of and try to stop with your body? Well, I think I could probably stop a tricycle. It might hurt, and I might get bruised, but I could do it. But there is no way I'm going to stand in front of a car rolling downhill and try to stop it. So the larger the inertia, the harder it is to stop an object. Disc B had the larger moment of inertia. So disc B, it has the larger rotational inertia. Disc B is going to be harder to stop, which is part of the idea behind things like turntables. I realize that most of you don't have records and you don't play them on a turntable, but really expensive turntables tend to be larger and heavier so that they have a greater moment of inertia. It takes a while to get them started rotating, but once they rotate, they stay in rotation. So they have a smoother play associated with them. And there are other things that rely on this. The turntable is just one example. Lots of things spin. All right, so the radius of gyration is sort of the average radius for an object. It's as if you had the mass concentrated at that one point. We could use it to calculate in calculations. It's a little bit like the rotational equivalent of center of mass. And in an equation, the radius of gyration is given by a lowercase k. We're not actually going to calculate with it. I just wanted you to know what it was if you see it in an equation. So let's see what we would calculate with. Let's look at these diagrams. So this diagram will be provided on a test. This diagram would be provided on a test. So we have the solid cylinder, that's kind of like the pencil. The hoop, well, this is a little bit like a bicycle wheel. A solid sphere, that's a pool ball or a bowling ball. Rod about the center, that's a propeller. Solid cylinder around the central diameter. I don't know that I've got any real world example to give you, but it's like you took a can and drilled a hole all the way through it around the rounded end and stuck a pencil through it and tried to spin it around that. The hoop about the diameter, well, it's the same hoop as the bicycle wheel, but now it's spinning. They make round vanes that go on. I've seen them on the tops of commercial buildings where they'll spin around and around. And then a thin spherical shell, well, that's a hollow ball. And then a rod about the end, that's a windshield wiper. All right, it's like a windshield wiper. Okay, so you can see they all have different moments of inertia. These are all capital I's for the moment of inertia. And you can see that the values for the capital I's vary depending on the shape of the object, but also depending on how you rotate it. So the rod, if it's like a propeller, we get this moment of inertia. The mass times the length you are from the center, the length of the object squared and then divided by 12. And then if it's like a windshield wiper, suddenly it's not 1/12, but it's 1/3. Or the ball. A solid ball and a hollow ball have different moments of inertia. Or the hoop that's like the bicycle wheel or like a ring, depending on how this one you're trying to spin it and this one you're allowing it to roll. So when it rolls, the moment of inertia is mr squared, but when you try to spin it, it's mr squared divided by 2. And the solid cylinder is way more complicated, as you can see. All right, so let's see, how would we use any of this? So again, depending on the shape and how you're rotating it, you'd have to come back to the diagram to find the actual mathematical version of I, the moment of inertia. So the rotational kinetic energy, remember that kinetic energy is mv squared divided by 2. So rotational kinetic energy, instead of mass, we have I, because moment of inertia replaces mass in our angular equations. And instead of v squared, we have omega squared, because omega is the angular equivalent of velocity. So rotational kinetic energy is I omega squared divided by 2. And it is measured in joules. Energy is measured in joules, even if it's rotational energy. So objects that rotate, and move. Translational motion is like you move down the road. You go from one location to another. You've undergone translational motion. So if an object rotates and undergoes translational motion, then the total energy is the kinetic energy of rotation plus the kinetic energy of translation. And we have a little example worked out for you where we pretend we've got a 20-kilogram log and we're going to let it roll down a hill. And we know how high the hill is, so that's our y, how high above the ground. We know the angle, we know how fast it's, and what we want to find out is how fast would it be going at the bottom of the hill if we let it start from rest. We know the log is 1 meter long and we know its radius. So if we go back up here, a log is rolling downhill would be this solid cylinder. So it's our very first diagram. So its moment of inertia is mr squared over 2. And in fact, we will put that in, whoa, what happened to it? Suddenly things went away. Where did my things disappear to? Uh-oh. I'm not sure how things disappeared. My over 2 disappeared from my equation, so we are going to have to add it. Oops, that's not what I want to do. I'm going to have to insert some things. Nothing seems to have worked out. So for the log rolling downhill, it's mr squared over 2. So we've got translational kinetic energy, which is mv squared over 2, kinetic, which is and rotational kinetic energy is I omega squared over 2. Potential energy is mgy. We know that linear velocity is r times angular velocity, so angular velocity would be linear velocity divided by r, and our total energy would be kinetic due to both translational and rotational plus potential plus lost energy or dissipated energy. We know the mass of the log, how high above the ground we're going to start, so how high is our hill, the length of the log, the radius of the log, and we're going to assume we start out at 0 velocity and 0 dissipated energy. So if we set up this equation, kinetic, the two kinetics plus the potential plus the dissipated at the top equals those same 4 things at the bottom. At the top, because we are not moving, the two kinetics are 0. And because we are not moving, we don't have any lost energy. So at the top, all we've got is potential energy, mgy. At the bottom, all we've got is kinetic energy, because there is no potential energy at the bottom, and we said we were going to ignore the dissipated energy. So that simplifies our equations, and now we've got just mgy equals mv squared over 2 plus I omega squared over 2. In equations like this, we want to get the 2's out of the denominator. I promise you, it's better to start out doing that. You could plug in the masses if you wanted to, and then there'd be one less thing to deal with. We'd have more numbers. It's kind of up to you on that. I'm going to show you how the masses cancel out though. So multiply everything by 2 to get rid of the 2's in the denominator. So 2 on the left, 2 with the first term, 2 with the second term. These 2's cancel, those 2's cancel. On the left, we've got 2 mgy equals just mv squared plus I omega squared. But we don't want I, we want its value, which is mr squared over 2. Remember, I had to fix that equation when we started out. And when we did that, we've introduced a new 2 in the denominator. So I would like to get rid of that, multiply everything by 2, all 3 terms. So the 2 on the left is there. This term has to be multiplied by 2, and then this term gets multiplied by 2. So this 2 and this 2 cancel. 2 times 2 is 4 mgy. This becomes 2 mv squared, and our 2's go away, so we have mr squared times omega squared. Well, what is omega? Well, we said earlier that omega, in our list of knowns, that omega is equal to v divided by r. So omega squared is going to be replaced by v squared over r squared. You'll notice that the r squares will cancel each other. Yay! So I've got 4 mgy equals 2 mv squared plus mv squared. Well, the masses all cancel. Or you could leave them in and write down the numbers, but the masses all cancel. So 4gy equals 2v squared plus, I could have written it as just v squared, but I chose to write it as 1v squared. 1v squared and v squared are the same thing. So 2v squared plus 1v squared is 3v squared. And now to solve for v, I divide both sides by 3 and then take the square root. So square root of 4gy over 3. And I wanted you to remember what the moment of inertia was, mr squared over 2. If we plugged in, we would get that the velocity for the log rolling down the hill is 16.166 meters per second. And it depends on how high is the hill and what is gravity, but not how long is the log, what's its radius, or even how heavy it is. Now, this is a perfect world because we ignored dissipated energy, but still, I think it's important for you to realize that the velocity is independent of the length of the log and the mass of the log. But the moment of inertia is not. It depends on the mass and the radius, and in fact, the shape, because that's where we get all those different equations. All right, let's see how those shapes compare. So if you've got a solid ball and a hollow ball, let's look at those two first. Solid ball, hollow ball, both balls. You can see their moment of inertias are 2 mr squared, but it's over 5 for the solid ball and over 3 for the hollow one. So over 5, the moment of inertia is going to be a smaller number. The moment of inertia is going to be a bigger number, if m and r are the same, for the hollow ball. What about those velocities? I'm not so good at seeing how 10 over 7 compares to 6 over 5, so I did as a numeric example. Hollow ball, solid ball, last numbers in the column. So for the hollow ball, it has the bigger moment of inertia. We talked about that. But it has the slower velocity. Bigger moment of inertia, slower velocity. Suppose we look at the two loops. A thin hoop and a solid log. You can sort of think of the solid log as being a very short, hollow, thin loop. I wanted similar shapes, but hollow and solid. And so you can see that the solid log has the larger moment of inertia. I'm sorry, smaller moment of inertia. Solid log has the smaller moment of inertia, just like the solid ball had the smaller moment of inertia. But you'll see how we'll see how our velocities go. So the one with the small moment of inertia had the bigger velocity. Just like down here, small moment of inertia had the bigger velocity. All right. So what happens? We see as the moment of inertia increases for a given shape, what's going to happen to the velocity? It decreases. It decreases. As the moment of inertia increases, so solid and hollow ball going from a small moment of inertia to a larger one. We went from a big velocity to a smaller one. Okay, moving right along. Angular momentum. So we had linear momentum was mass times velocity. Angular momentum is going to be the angular equivalent of mass. That would be moment of inertia times the angular equivalent of velocity. That would be angular velocity. So angular momentum is moment of inertia multiplied by angular velocity. We symbolize angular momentum by a capital L. I don't know why they picked that, except L looks like the symbol we sometimes use to indicate an angle. So L equals I omega. Angular momentum equals moment of inertia multiplied by angular velocity. It is measured in kilogram meter squared radians per second, or remembering that a radian is not really a unit, you could call it kilogram meter squared per second. Linear momentum is mass times velocity. Remember, I just said that. And in fact, if we remembered that when we first introduced Newton's second law, F equals ma, we said you could write it in terms of momentum, F equals delta P over delta T. So instead of F, we do tau for torque, because torque is the angular equivalent of force. Instead of delta P for linear momentum, we'd use delta L for angular momentum, and delta T is delta T. This is an example of taking a linear equation, F equals delta P over delta T, and turning it into an angular equation. Tau equals delta L over delta T. If I gave you a made-up pretend linear equation, you ought to be able to write the made-up pretend version of it as an angular equation, knowing that taus replace f's, l's replace p's, omegas replace v's, i's replace m's, and so on. Okay, we'll have some practice problems, maybe. Law of conservation of angular momentum tells us that the angular momentum of a rotating body remains constant if the net torque acting on it is 0. So how does that help us? Well, let's look at an ice skater. So an ice skater is starting out with her arms out, and then she brings her arms in. So we have before with the arms out, after with the arms in. So the and we've said with law of conservation of angular momentum, that angular momentum remains constant. So angular momentum before equals angular momentum after. Angular momentum before equals angular momentum after. So L before equals L after. But L is I omega. I for mass, that's the moment of inertia, and omega is the angular velocity. So I omega before equals I omega after. I omega before equals I. This is supposed to be a capital I. I know it doesn't seem to look like one, does it? It's supposed to be a capital I. So I omega before equals I omega after. And I is the sum of all the mr squared. So mr squared omega before equals mr squared omega after. So what have we got with our ice skater? The mass doesn't change. If she's skating, the mass in the left diagram and in the right do not change. The mass does not change. But the radius does. If you look with her arms out, r has to be a larger number. When she brings her arms in, r becomes smaller. So we go from a large r to a small r. And the masses stay constant. Well, if we go from a large r to a small r, but we have to keep them equal, that means we have to have an increase in our angular velocity. An increase in our angular velocity. So as you reduce r, omega is going to go up. And we use this in all kinds of different ways, especially in athletics. So a diver or an acrobat, the tighter they can make the tuck when they try to do a somersault of some sort. So the smaller the R, the larger the omega. So the faster you're going to spin. This is important, like if a diver, you're trying to do 2 or 3 rotations in a tight tuck, so that then you can open up and enter the water at 90 degrees to the water. You need to spin relatively fast. So a tight tuck. We've got a rotating platform in the lab, and we will use it. You're going to sit on it with your arms out and spin, and then bring your arms in and spin, and we will see what happens. So we have this in lab. We'll do it as part of a lab. And that finishes our chapter.